I'm going to start the recording. Okay, so to know if something's independent, that's the definition. And this is going to be in your assignment also, assignment 3. So if it's independent, it means, and I'll talk about the symbol in a minute, it means B, event B has no effect on A. So what these symbols mean right here, what I just wrote, is the probability that A happens given that B happens. So that straight line means given, and it's conditional, and that's really important. So I'll keep going, but it's the probability that A happens given that B happens is equal to the probability that just A happens. So if that's true, if we know that A happens despite B and A happens anyway, then that has to be independent. This means B has no effect on A. All right, so this straight line right here, it means given. And so this is the part that's the condition. We know B happens. So what happens is that makes the sample space smaller. Okay, because it has to come out of B, since we know B happens, then it's saying, well, what's the probability that A happens? So if the probability of A given B is the same as just the probability of A anyway, then that means B doesn't matter. B has no effect. So that would make A and B independent. So that's what they're asking you in this problem. So let me write down the numbers you had. And your problem was, I think it was aerospace. This is to see and connect. Aerospace, and it was low risk, and then moderate and high risk. And there was 16 here, 17 here, and these are companies. And then we had food companies. And I think it was, I can't even read my own writing. Let's just say 21 and 38. So we want to show aerospace company, aerospace, and low risk are independent. So that means that a low risk company doesn't depend on if it's aerospace and vice versa. So what that means is that we want to find the probability that it's aerospace given low is just the same as if it was aerospace anyway. Low risk has nothing to do with it. So those two would be independent. All right, so let's look at this side of the problem first. Just the probability that's aerospace. So we would add all these companies up. So we would add to get the total. So let's see, the total number of companies would be 16 plus, and jump in if you don't understand, 16 plus 17 plus 21 plus 38. So that's 92. So let's say the total of all these companies is 92. And all I did was add all these numbers up. So the probability that it's aerospace would be right here. Aerospace going across would be 16 plus 17. So that would be 16 plus 17 would be aerospace. That's 33. So the probability, and I guess I should have talked a little bit more about probability, but probability means, and this is how I like to think of it, is the chances that, or the number of ways you get what you want over your total number of choices. So the number of ways that we could pick an aerospace company would be 33. There's 33 aerospace companies. That's 16 plus 17. This, and this are aerospace over your total, which is 92. So on a calculator, that would be 0.3587 if we go 4 places. How many places did they? Let me check a minute and see.
Yeah, it was 4 places.
4 places? Okay, yeah, 4 places. And every time you work this problem, the numbers change, but that would be that part of it. And you got that part right. Okay, so let's look at the other side. It's easier for me to just erase this instead of rewriting all the numbers. So we have, I'm just trying to get more room. We have that side of the equation. Now we need the probability of A given L. So the formula for that is it has to come out of the low risk companies, because this is a probability that it's aerospace given that it's low risk. So it has to come out of the low risk. If we know this, again, this is the given part. This is what we know. This is what it has to come out of. So the given part is always in your denominator. And your top is the probability that they're both. I'll draw you a picture in a minute of what that would look like. But that's the formula for conditional probability. So the second part, given that it's low risk, so we know it's low risk, that's what our new total is. That's our new sample space. So that is in our denominator. That's our new total. And then the probability that it's both would be on the top in the numerator. So this is equal to add up all the low risk. So let me change the color here so I don't get messed up. Low risk is right here. So it's coming out of that set of 16 plus 21. So on the bottom would be 16 plus 21. That's the chances or the total that it's low. And then out of that, it has to be an aerospace company. So an aerospace and low is 16. So 16 would be on the top. Does that make sense?
Yes, it does. Thank you.
Okay, so that would be 16 divided by 37. And on a calculator, again, I'll draw you a picture of conditional probability because that's really important this week. 4, 3, 2, 4. So that would be the the conditional part, and you can see those two numbers aren't equal, so they're dependent. They're not independent. But let's before we do that, let's talk a little bit about conditional probability. So we have set A, and let's say set B, and they overlap. And I want to draw a picture of A given B. Okay, so I wanna show you where that formula comes from. And again, it looks like the symbol looks like that. Okay, so if you read in a problem that what are the chances or the probability that A happens given that B happens? So since we know that B happened, it has to come out of this set right here. That's B. Okay, so this is our new sample space or our new total. It's not the whole thing anymore. It's our new sample space. Okay, so we don't care about over here. We only care about what comes out of B because it says given B. So that tells us that we know it's coming out of set B. Well, what are the chances that A happens knowing this? So if we look at this, where is A in this picture? A is right here. Okay, A is part of that circle that's inside B. So this is the part of the circle of A that is inside B, and that is where A and B meet. This is A and B. So that's why it has to come out of B. So your denominator is the chances it comes out of B, and your numerator is the chances it comes out of A and B at the same time. This overlap part is A and B. So that's a picture of what's happening. And this is called conditional probability. And I guess while we're here, we could, I'll just do another example. Let's say we have a deck of cards. And we know we have 4 suits. We have 13 clubs. We have 13 spades. We have 13 hearts. And we have 13 diamonds. These are black. And these are red. So we have 52 cards in a deck of cards. So suppose we pick one card. What's the probability it's a let's say diamond given, well, let's just start there. Okay, let's just go back to the basics. What's the probability it's going to be a diamond? Well, again, I just want to go back to the basics. Probability, the way I like to think about it, is the number of ways we get what we want. You always get what you want. Over the total number of ways that you can perform that experiment. So the number of ways that you can get a diamond are 13, and there's 52 cards. And if you reduce that, you get 1/4, which makes a lot of sense because 1/4 of the deck of cards are diamonds. But if you want to do the conditional probability, let's practice that. What's the probability that you get a diamond given that it's red? given that it's red. So we know it's red. So the number of red cards is your new total, has to be in the denominator. Okay, so your red cards is in your denominator, or your new total, because it's not coming out of the whole deck anymore. It's only coming out of the reds. We know we got a red when we have this line here. Again, that means given. So how many red cards do we have? Well, we have 26 red cards. It's not coming out of 52 anymore. Okay, because somebody told us, or yeah, we were told that we only had red cards. It was given that it's red. Okay, and in the numerator, this would be the chances you get a diamond out of those red cards. So it has to be red, diamond and a red. Well, diamonds are red, and there's 13 diamonds in a deck of cards that are all red cards. So this reads 2.5. And actually that makes sense too, because you have 13 diamonds and you have 13 hearts. So half of those would be diamonds for your red cards. Okay, so does that kind of help with the given part?
Yeah, that makes total sense now.
Okay. Did you have any other questions?
I don't right now, but I definitely want to hear more.
Okay. Yeah, I'll start from the beginning. We kind of jumped into it. I'll go through and do some more examples. Hi, Charity. Do you have any questions before I do examples?
No, just whatever examples that you can give.
Okay, well, jump in if you need anything like specific, okay?
Okay, so far I'm following. What's been a struggle for me is making a real world connection so I can make it make sense, which is why I struggled. Sorry. Which is why I struggled last week with the rules and all that stuff, because I couldn't like attach it to a real world example that made sense for me. But like this one I understood when you drew the diagram and then explained with the cards.
Okay, that's what I'm going to try to do. We'll just stick with the cards and draw pictures so you can see what's going on.
Thank you.
Okay, so jump in. If you have any questions, like I said, I'll just continue doing some examples. So again, let's just stick with the cards, and I wanted to do some, let's go back to the basics and then work our way through the formulas. So again, we have 52 cards. What's the probability that it's a king? And you're picking one card. So that's really important. You need to know how many experiments you're doing or how many events. So we're going to pick one card, and what are the chances we get a king? Now, a lot of people think that, well, since you're only picking one card, it's going to be 1 out of 52. But the way you think about it is you always have to think that you get what you want. And you have to think about how many ways you can get what you want. So if you want a king, there are 4 ways to get a king. There's a king of diamonds, a king of hearts, a king of clubs, and a king of spades. So there's 4 ways to get a king out of 52 cards. And again, that just reduces to 1 out of 13. What about probability you get a black card? Well, you should say right away half. Well, half the deck's red, half the deck's black. But the other way to think about it is how many black cards are there? Well, there's 26 cards that are black out of 52, and that reduces to a half. Half are black, half are red. And then let's just look at probability to get a heart. Well, there's 13 ways to get a heart. Even though you're only picking one card, you have to think about the number of ways that you can get that heart. And again, we have 52 cards, so that's 1/4. And that should make sense too, because there's 4 suits: hearts, clubs, diamonds, and spades. So out of one of those 4 suits is a heart. So 1 suit out of 4 are hearts, 1/4. All right, then we can travel into talking about mutually exclusive. Now, all this means is that if 2 events are mutually exclusive, they do not overlap, or they do not intersect. So you would just have 2 sets that are separate like that. That would be mutually exclusive. If they overlap, then they're not mutually exclusive. Okay, so if I want the probability of a red and a queen, okay, let's talk about the word and. And again, if I'm going too fast, or if you have questions, just stop me. Okay, I just have some examples that I'm gonna talk about, because the wording is kind of, it's not tricky, but you just have to read it carefully. In this case, you have to remember that we're picking one card. So this would be red and a queen both at the same time. So in this case, if you draw a picture, we have the red cards and we have the queens. And these 2 do overlap. You can have a queen and it be red, and that would be the queen of hearts and the queen of diamonds. So there's 2 ways that you can have a red queen both at the same time. So the probability of that happening would be 2 out of 52. So these 2 events are not mutually exclusive. Now here's an example that is mutually exclusive, would be a black card and a red card. They don't overlap. You either get a red or you get a black. These are mutually exclusive. These are not. So the definition of mutually exclusive is just, do the sets overlap or do the sets intersect? And that's all there is to that. Can they both be the same thing at the same time? All right, so that's the word and. And means both at the same time for one event or one choice, one pick. And if you're picking more than one card, then the word and means something different. So we'll talk about that one in a minute. But right now, if you're picking one thing and you have the word and, then it has to be both at the same time. So let's go to the word or. And or means add. So again, remember, we're still picking just one card. So what's the chances that we get 10 or a jack? Now these are mutually exclusive because the 10s are over here and the jacks are over here, so they don't overlap. So they're mutually exclusive. So in that case, you're going to just add these two together. What are the chances that you get a 10? Well, there's four 10s and there's 4 jacks out of 52 cards. So there'd be 8 ways out of 52. Or if you reduce that, let's see, that would be 2 out of 13. So if they're mutually exclusive, you would just add those two together for the word or. But what if they're not mutually exclusive? So what would happen? Okay, what would happen if you want the probability of a club or a queen? Again, one card. So these are not mutually exclusive because you could have a queen of clubs. So they're not mutually exclusive. What we have to watch out for is that we don't count anything twice. So you're going to add up the clubs. So there's 13 clubs. And then there's 4 queens. But what's the problem? There is a queen of clubs. So we counted the queen here in the clubs, and we counted the queen here of clubs. So we have to subtract one of those out. We have to subtract out the queen of clubs. So I'll write that formula for you. But if they're not mutually exclusive, then you end up counting things twice. And so we want to take out one of the queens of clubs. Okay, so again, we counted it here. We counted it here. We want to take one of those out. So at least we counted it once. So we subtract it out. So the formula for that, if they're not mutually exclusive, or means add, but you subtract out where they're both the same at the same time, where they're, I'll just say both. So you don't count it twice. So again, when we count the 13 clubs, we counted the queen of clubs. When we counted the 4 queens, we counted the queen of clubs. Well, we only want to count it once. We have to subtract out the queen of clubs, which is, it's both a queen and a club. And so we take out one of those and make sure we just count it once. So this is the formula that we use for the word or. Okay, let me write that out. Let me write it out again. So the probability A or B would be the probability of A plus the probability of B if they're mutually exclusive, which means they don't overlap. If they are not mutually exclusive, then you have to subtract out the part that they're both so that you don't count anything twice. Remember, if they're not mutually exclusive, they overlap. So you don't want to count that middle part twice. Okay, so that is the word or, the formula for or. Now let's talk about and again. Let's go back and talk about and. Okay, if it's one choice, you're only picking one choice, then and means both at the same time. But if you're picking 2 or more, then it means multiply. So what I mean by that is this time we're picking 2 cards, and I want the probability that I pick a 10, then a jack. So I want a 10 first, and then I want a jack. So basically this is 10 and jack. So the way I like to think about this, there's two ways to do this: with replacement and without replacement. Okay, again, jump in if you have questions. Okay, so with replacement means once you pick a card, you put it back. You replace it. You put it back in the deck. So if you start with 52 cards and you pick it with replacement, you put it back on your next pick, you still have 52 cards. Without replacement means you pick a card. Okay, so you had 52 cards and you picked a card and you keep it, then on your next pick, you only have 51 cards. So without replacement means you pick it and you don't put it back. So you always have one less. Okay, so let's do it both ways. And I like to do it with fill in the blank. So I do 2 blanks because I'm doing 2 cards. So this is my first pick. And means multiply here. My second pick. And I do it the same for this one too. First, and means multiply my second pick. So I do them both the same way. The only difference is when I keep it, the example set goes down by 1. All right, so my first pick, I need a 10. So first I get a 10. So there's 4 10s out of 52 cards. And with replacement means I'm going to put it back. So that means I'll still have 52 cards. But now I want a jack, and there's still 4 jacks in the deck. So it'll be 4 jacks still out of 52 cards. So this will be 16 over 52 times 52. I'm not going to reduce that because we're just talking about how to get there. Okay, now on the second time you do this, you're going to take a card, but you're going to keep it. So you're going to have 4, there's still 4 10s when you start. You're going to start the experiment. You want a 10, well, there's 4 of them in the deck out of 52 cards. But you're going to keep that 10 out of the deck or out of your choices. So you only have 51 cards left because you're keeping it. You're not putting it back. And there's still 4 jacks because you got a 10 on your first pick. You didn't get a jack. So there's still 4 jacks. So that's going to be 16 over 52 times 51. Okay, let's try another one because you have one of these in the discussion answer questions. Of course, they're not cards, but how about this is the same problem. You're picking 2 cards. What's the probability that you get 2 10s? A 10 and a 10. With replacement means you pick one, put it back. Without replacement, and they have to tell you which way they're doing it. I mean, I guess if you're picking people, you're not replacing them. You're not going to pick that same person twice. So that would be without replacement. So if you're picking people, it would be without replacement. But here we're doing cards. Okay, so we want a 10 and a 10. And remember, and means multiply. When we pick 2 cards, 10 and we want a 10. Multiply them. Okay, well, there's 4 10s in a deck. Again, 4 10s in a deck. So there's 4 ways to get what you want on your first pick out of 52 cards. And if you put it back in, there's still 4 10s out of 52 cards. But here, if you keep it, like we're going to do in the discussion problem, we're keeping that person out because you're not picking it again. We have 4 10s. We have 4 ways to get a 10 out of 52 cards. But when you don't put that 10 back in, okay, you got a 10 on that first pick. So now there's only 3 10s left because you didn't put that 10 back. So that's going to go down by 1, and your total is going to go down by 1 because there's only 51 cards left. So when you always assume you get what you want. So on that first pick, you got a 10. You don't put it back. There's only 3 10s left. So the first one would be 4 out of 52, but the second one would go down. Notice when we had the 10 and the jack, it didn't go down because we got a 10. There was still 4 jacks left. But if you want the same thing, then that has to go down by 1 because we want a 10 and we got a 10. So that's the difference between with and without replacement. And I think there's one more. Go ahead if you have a question. Questions? Any questions? Okay, there was one more formula. It's the complement formula. And this is the probability that you don't get something. So I think we could say the probability that it's not red. One card. We're picking one card. What's the chances it's not? Let's do a different one because they're either red or black. Let's try a different one. Let's try not a heart. Okay, so remember there's 13 hearts. So if there's 13 hearts, the way to think about it would be subtract that from 52. Well, 39 are not hearts. So that would be 39 that are not hearts out of 52, or 3/4 of the deck are not hearts. Well, the reason I wanted you to think about this is because the formula for this is probability not A is 1 minus the probability that it is A. Okay, this is the formula that we use. And that should make sense because 1, see how we subtracted it from 52? That was our whole. 52 is our whole. And 1, or 100%, which is the same as 1, is our whole. So we take away the, if we want the probability that's not A, we take away A from the whole. And a picture of that, I guess you could say, is here's A and here's not A. So if we take this whole thing, which is 100%, and subtract A from it, then what we get is not A. And that's called the complement. So the way to think about this would be 1 minus the probability it is a heart, which would be 1 minus 13 out of 52, which would be 52 out of 52 minus 13 out of 52. Which is 39 out of 52. So you get the same answer using the complement formula. So that's pretty much everything that, all the formulas that you need to know. Let me just summarize them. Okay, so probability of A is number of ways to get what we want, which is A. So to get A over the total number of ways. Okay, so that's the basic probability. Probability that it's A or B is addition if it's mutually exclusive. If it's not mutually exclusive, then you have to subtract out the part that overlaps. Okay, so if you just joined us, I've covered all these formulas. Probability of not A is 1 minus the probability that it is A. And probability of A and B is probability of A times the probability of B. if they're independent, and if there's two events. All of this is for one event. And then, conditional probability is the other one. Probability that A given B is the probability of A and B both over the probability of B. And I think that's the definition of independent, I guess. Independent, let me squeeze that in here. Definition of independent is if the probability A given B is the same as probability of A. That means B has no effect on what happens to A. If those two are equal, then B doesn't matter. Okay, so I mean that's kind of quick, but those are the kind of I did those other videos too, and I have more examples. But if there's something that you're stuck on, I can go over, make up another example if you need it. Is there anything that you might want to see some more of?
This is Marion. I'm not talking about the examples and stuff, so I have that part. But I was looking at our assignment for this week,
Okay. Uh-huh.
and then so on it says to with the red and green. Suppose that you have a box of red marbles and green marbles. You draw 3 out of the box, but it doesn't state how many is in the box. So I was a little confused there.
Oh, wait a sec. Oh. Is that number 1?
Yes, on week 3 assignment. Yes.
Oh, and you have red and green balls?
Yes.
You don't have to put the numbers on that. Like that would just be the same as like if you had a boy or a girl. You don't have to put the number. I mean, yes, usually that's a good question. Usually in a tree diagram, yes, you put all your numbers in, like the chances of having a boy is a half, chances of having a girl is a half, and then you make your branches. But you don't have to do that for that. All you have to do is do the, okay, you could get a red or a green on the first pick. On the second pick, you could get a red or green after you get a red, and then you would do one more branch. That's all you have to do there.
Oh, okay. Okay then. All right. After 3 times, you do that 3 times.
Yes, but that's a really, really good question because, you know, if you had the numbers of balls that you had, then you would actually put the numbers there.
Okay.
But we don't have the numbers, so you don't have to.
Okay. I got it. Thank you.
No, really good question. Yeah. So like if you say you had 3 red and 5 green, then the chances you would have a red on the first pick would be 3 A's, and the chances you had a green would be 5 A's, and then you would do that for each branch. And again, we don't know if this is with or without replacement, so we really, you know, can't go any further with that. But that's a really good question.
Okay, thank you.
Okay. And then to get it into your document, all you have to do is take a picture of it and insert it. That's just one way. I mean, any way will work. Any way you want to put it in the document. I just made a suggestion. But yeah, really good question. Thank you. Anything else? Okay, if you end up having more questions, just email me. Okay, I mean, again, you can call or text me, but contact me. There isn't any small question. If it's something that you need help with, I will help you.
Thank you much.
Yeah, we pretty much talked about everything. I'm looking at the assignment. There is the binomial theorem. I'm not going to do a problem right now on it because we did go over so much tonight. The video I made is really helpful, or the video I posted, there's another person that is working examples, and if you work these in Excel, they're so much easier. So a binomial experiment has a success or a failure. So it's, good, bad, success, fail, yes, no. There's always two outcomes. And you can work it longhand. And in the video, I showed how to do it longhand, but it's much easier to do Excel. So I think if you watch the video, it's real short. It's not long. If you watch that, it shows you how to do the problems. If you still need help on it, I can jump on and collaborate. So you just have to let me know. Just let me know when you need help. Okay, will that work? Because I think it's real clear. I don't have anything else to say about it unless you watch it and you still don't understand it. So I want to give you a chance to look at that. And if you still are having problems, please don't hesitate to let me know, and I can get on and help you with that. All right, well, I guess one last chance. Any questions?
No, just a comment actually about that binomial distribution video you created.
Oh,
The hyperlink, you just need to add an H to the hyperlink because the link fails because the H is missing out of the HTTPS. No problem. I was able to figure it out, but just in case somebody else wasn't.
No, I'll fix it right away.
Perfect.
All right. Thanks for letting me know. Did it work though after that?
Oh yeah, absolutely.
So were you able to figure it out from the video?
Yes. Thank you.
Oh, okay. Good. Well, I mean, if you still need help, let me know and I can get on again because we still have time this week.
Perfect. Thank you. Have a great week.
All right. You too. All right. Have a good night, everybody. Let me know if you need help. I'll be posting this video